be achieved using this new technology. To start, I'll give a brief introduction to Intel Optane DC persistent memory. I'll talk about some of the concepts we have for enabling this new technology. We'll talk about workload suitability analysis. How can you look at your existing workloads to determine whether persistent memory would be a good fit for them? And then we'll talk about profiling these workloads, what sort of performance metrics are important, what you should be looking for in order to get the best performance on your specific workloads, and we'll finish with some case studies. If anyone has questions, feel free to ask questions. I have my colleague Jan here who can help translate, so if you're more comfortable asking questions in Chinese, that's no problem. He can help translate, and we'll make sure you get the information you're interested in. All right, let's go ahead and get started. So what is Optane DC persistent memory? It's a new memory technology, and in this case, it's in a DIMM form factor. So it works over the DRAM slots that you have. And it has both attributes of DRAM and SSDs, right? It's persistent, like solid-state drives, but it's also much faster than your typical disks, which makes it similar to DRAM. It's based on this new Optane media technology, and it can be used in a storage mode or in a memory mode. The way that you use Optane DC persistent memory is up to you. And these programming models are selectable after you've got the system set up. You can choose which way to use the Optane DC persistent memory. If you imagine the existing machines that you have without Optane technology, you've got this legacy platform here, where the main memory is all of DRAM, right? You have your caches, you have your DRAM, and you have your disks. And you know that DRAM is slower than caches, and disks are slower than DRAM, right? This new technology, Optane DC persistent memory, extends the platform with a new memory. And you can use it in one of two modes. The first mode is memory mode. In memory mode, the persistent memory just looks like system memory. And the benefit here is that this new memory is much larger than DRAM. Particularly from a cost perspective, the cost per gigabyte is much lower. So you can have much more system memory on a platform with this new technology than you could before at the same price. Memory mode is completely transparent to the programmer. If you have a machine with this technology in memory mode, it just looks like you have maybe 1 terabyte of memory available, right? All of your dynamic allocations, all of your freeze, all of your heap memory, it's just automatically going to use Optane DC persistent memory without your programmers needing to change anything. That's what memory mode is. The other mode is App Direct mode. In App Direct mode, you have your DRAM memory as one option, and you have your persistent memory as another option. And the programmers choose where to allocate each object. You can allocate an object in DRAM, which has the lowest latency, or you can allocate an object in persistent memory if you need persistence through power cycles or something like that, or if you need larger size, right? The persistent memory is going to be larger, so you may want to allocate objects there. There's also the ability to mix. You know, if you have a lot of Optane DC persistent memory, you can configure some of it in the memory mode and some of it in the persistent mode, so that's available as well. Some questions to think about whether your application will benefit from Optane DC persistent memory. Do you need big memory? Are all of your workloads running out of DRAM, or are you buying very expensive machines to have enough DRAM available to your workloads? Do you need fast storage? Are your bottlenecks related to disk accesses? Do you have performance issues because reading from disks is so slow? Do you need memory resilience? This is specific to the persistent aspects. If you have a lot of performance issues after power cycles in a database or something like that, then persistence will be very important. So if you're running out of DRAM, have large I/O latencies in your application, or warm-up and data population through a power cycle because your data is not being persistent. Those could all be cases where Optane DC could help. It's important, so some people may know automatically the answers to these questions, but many people are not experts in the workloads that are running on their systems, right? Maybe you are a cloud provider and people bring their workloads. You may not be an expert on the workload. So it's important that you have tools that help you answer these questions. You know, how is my system and the applications that are running on them performing? How could Optane DC persistent memory help me? And there's a lot of ways to answer these questions, but the easiest way to do it is to use some sort of tool that already has built-in expertise. And at Intel, we have those tools. And I'm going to show you a little bit about how you could use them, and I encourage you to try it out. If you've attended some previous sessions or you were in the keynotes, you've probably already heard of Vtune Amplifier. This tool's been around for a long time, and it's a very powerful performance analysis tool. You can analyze the CPU, you can analyze the memory, you can analyze the disks, and now with this new technology, we've added features to analyze Optane DC persistent memory. There's a feature called Platform Profiler that I'll be talking about more to help you find the best configuration for your system. And there's built-in performance analysis types as well. We have a memory analysis and a storage analysis. If you are using Optane DC for persistence, and you need to make sure that you're doing persistent programming correctly with something like PMDK, we have a correctness tool called Persistence Inspector. This one will help you analyze your application to figure out if you're doing persistent programming correctly. It's not automatic that your persistent programming will be correct. If you don't flush your memory properly, you can have correctness issues that need to be debugged. So with a tool like Persistence Inspector, you can easily debug those type of problems. Next, I'll talk about some of the use cases we have. We have use cases for our tools in two situations. One that many of you may be in today is before you have hardware, meaning before you have Optane DC persistent memory on your platform. There are still lots of things you can do to figure out whether you can benefit from this memory technology. We'll help you understand what you can do when transitioning from a DRAM-only system to memory mode. We talked about briefly what memory mode is, and also transitioning from a DRAM-only system to app direct mode, where you're manually choosing which objects to put in DRAM and which objects to put on the Optane DC persistent memory. In addition to this suitability analysis, which is what we call this section up here before you have hardware, we have lots of powerful features for analyzing applications that are running on platforms with Optane DC persistent memory. I don't know how many of you spend time optimizing performance, but if you do, you know that it's challenging. Just like debugging a program for correctness, optimizing a program for performance is very challenging as well. And having tools to help you do that makes your job a lot easier. I won't spend too much time on this slide because I think in the keynote you've had an introduction to Vtune already. But if you've never seen Vtune or never used it, this is a really quick introduction. It is a very powerful performance analysis tool that supports lots of different workflows, lots of different use cases, and lots of different environments. We support many different languages, more than that are just listed here, and many types of workloads. Whether you have MPI in a cluster environment, or you're running in a virtual machine in a cloud environment, and you're running Python or C++ or some other language, the chances are that Vtune can help you analyze your performance. It's very easy to set up. You can get data very quickly, even if you're a beginner. It's free for anyone to download and install. There's a hands-on session tomorrow if you want to learn more. I encourage you to do that as well. And it has cross-OS support. So what that means is, if you have a Linux machine running in the cloud and you want to analyze the performance, you can run a very lightweight collector on that machine, copy the results over to your Windows laptop, and do all of the analysis there. You don't have to analyze the data on the same machine where it was collected. So you can share results with colleagues. If they're on Windows and you're on Linux and your friend's on Mac, that's no problem, right? It doesn't matter the platform that you do the collection on. The analysis can be done on any other platform. Platform Profiler is one of the features we have inside Vtune Amplifier. This one's going to give you a very high-level view of the performance of your platform. This one's not designed for tuning a very specific application. This one is designed for seeing things like the topology of a server. Where do you have the disks connected? How are your DRAM slots populated, right? A lot of times performance issues could just be related to the configuration of the system. And all it takes is moving one disk from socket 0 to socket 1, and you can relieve a performance bottleneck, right? So understanding the configuration is very important. We have performance metrics built in for the memory, the storage, the CPU, the PCIe buses, and all of that is displayed on overtime timelines that you can see here. So things like low CPU utilization, if you have NUMA performance issues with a lot of communication between the sockets, Platform Profiler can help you identify those as well. Now let's talk about the suitability analysis. What can you do for transitioning to Optane DC persistent memory today? Maybe you don't even have any hardware, right? But you want to understand whether your workloads could benefit from this new technology. The first mode I'll talk about is memory mode. Memory mode is the mode that's easiest to use. In memory mode, all you do is plug in these new DC persistent memory DIMMs into your platform, and all of a sudden, your machine looks like it has tons of memory, right? Maybe before you had 128 gigabytes of DRAM, and now you plug in 1.5 terabytes of Optane DC persistent memory, and all of your applications see 1.5 terabytes of memory. Your coders don't need to change anything. There's nothing that needs to be done with allocation. It's all done automatically. And this mode is very useful for applications that require lots of memory, right? And one way you can determine if your applications need lots of memory is with our Vtune Amplifier memory consumption analysis. There are many tools that can do memory consumption analysis, but this is the one that we offer. The memory consumption analysis in Vtune will show you over time how much memory is being allocated by your applications. It will show you the allocation sites where the memory is being allocated, and as things are being deallocated, the memory consumption will go down. What you're looking for is the peak memory consumption of your workload. If your workload is consuming somewhere close to 100% of the available DRAM, chances are that this workload could benefit from more memory, right? If your workload is only consuming 10% of the available DRAM, you don't need more memory. So that's not the bottleneck in your code. But you want to identify whether memory size is the bottleneck. So we have a memory consumption analysis to help you do that. After you do a memory consumption analysis, it's important to understand how large is the hot working set of your application. That's different than the total amount of memory consumed. The hot working set is the objects in your application that are accessed very frequently, right? So you might have an application that allocates 100 gigabytes of memory, but really it only works on a 1 gigabyte table of data frequently. Everything else is used very infrequently. So you have a hot working set of only 1 gigabyte, right? And that's important to understand because for memory mode, you want to look for applications that have a large memory footprint, so they're consuming almost all of the memory, but their hot working set is actually small. In those cases, automatically, those hot objects will fit into DRAM. And DRAM is lower latency than this persistent memory. So those are the kind of characteristics you want to be looking for if you're going to be using memory mode. Any questions about that? Okay. Sure. Yeah, just feel free to raise your hand if you have a question or if something is included. You can also do a memory consumption analysis with the platform profiler feature in Vtune Amplifier. Here I'm just showing you a different way to do a memory consumption analysis. Platform profiler has a few characteristics that are different than the other memory consumption analysis that I showed. Platform profiler always profiles system-wide. It has the ability to profile longer running workloads. If you have workloads that are taking hours and hours and hours, this is the type of analysis you want to do. And as I show you more about Platform Profiler, you'll see how you can correlate this metric with other metrics that we collect also. So memory mode is the easiest mode to use. It's totally transparent to the software developers. They don't need to change anything, and automatically they see a large amount of memory available on the system. But it isn't always the mode that gets you the best performance. If you really care about getting the best performance, you may need to investigate what's called App Direct mode. In App Direct mode, the user has to manually specify which objects get allocated in DRAM and which objects get allocated in Optane DC persistent memory. If you've used other platforms with different types of memory on them, you may be familiar with this concept. Maybe something like a high bandwidth memory, and you manually allocate in that memory or DRAM. In App Direct mode, you use APIs to choose where objects are allocated. And we have some advice in our tools to help you understand how to do this. You don't have to do it all on your own. The key characteristics that you want to look for when targeting App Direct mode are the size of the objects that are being allocated. And if you run a memory access analysis in Vtune, you'll be able to see the size of every object that's allocated, and from there you can choose where to put those objects. What you want to be looking for is objects that are larger than DRAM will obviously need to be allocated in persistent memory. They won't fit in DRAM, so you wouldn't allocate them there. If an object is very small, it's also okay to allocate it in persistent memory because the chances are those objects will automatically be brought into the lower level caches, your L1, your L2, your L3, and so they won't be accessed from memory very often. The most important thing to think about when choosing where to allocate your objects is what we call hotness of those objects, right? How often are they accessed? And with Vtune, we can actually collect that data. Here you're seeing all of the objects that were allocated in an application and all of the loads and stores that occurred to those objects, right? We can count those with our tool. You want to find the objects that have the highest number of loads and stores and last level cache misses and put those in caches or DRAM. DRAM is the fastest memory on the platform. It's faster than Optane DC, but it's smaller. So you want your hottest objects in caches or DRAM. Your next hottest objects that won't fit in the caches or DRAM can go in the Optane DC persistent memory, and then the cold objects that you have that are accessed very rarely, it's okay for those to sit out on the disk, right? So essentially what we're showing here is the guidance that you can get with our tools when trying to do App Direct programming. I don't know how many people here are familiar with App Direct programming, but if you're not and you start reading about it and your manager tells you you need to go investigate this, remember that there's tools to help. You're not on your own. You don't have to do it all by yourself. Another consideration when using Optane DC persistent memory is related to the latency of loads versus stores. One characteristic of this technology is that the loads are much faster than the stores. The reads are much faster than the writes. So when considering what objects to put in Optane DC persistent memory, it's important that you evaluate the loads in the stores. I already showed in a previous screenshot that we can calculate those with our tools. So another thing to consider is that you want to put store-heavy objects in DRAM. The store-heavy objects will be affected more by the write latency of persistent memory. The load-heavy objects are better candidates for Optane DC because the load latency is less than the store latency. Both of those techniques that I was talking about were related to getting performance out of DC persistent memory, regardless of whether you need the persistence aspects, right? Many people will have applications that want to use Optane DC persistent memory as storage, or they need persistence out of the data. In that case, you should be profiling your application and looking for storage-related performance issues. With Vtune, we have an I/O analysis that will collect I/O wait time. The I/O wait time gives you an idea of how much performance you're losing because of disks. If you're losing a lot of performance due to storage and due to the disks on your platform, Optane DC persistent memory can help, right? You can use this in a persistent mode as storage, and it's much faster than many other storage solutions. So if you know right now that the workloads running on your platforms are bottlenecked by storage, this is worth investigating. If you know right now that the application you develop is bottlenecked by disk, this is worth investigating. Figure out whether Optane DC persistent memory could alleviate that bottleneck, right? It may be able to get rid of the bottleneck you're currently seeing related to disks. This previous slide here shows you an analysis that you can do with Vtune Amplifier called Disk Input and Output. You can also do an analysis with Platform Profiler. Platform Profiler is showing you metrics related to your disks. You can see here the throughput for a disk attached to the system. And another important metric is actually page faults. If you have swapping because you're running out of DRAM and data is being swapped in and out of your disks, not because you're writing to storage, but because the disks are used as swap space, you'll start seeing these page faults. And that has a huge performance impact. If your applications are running out of memory and causing page faults, you need more memory, and Optane DC is one way that you can get more memory. Those are all things everyone in this room can do today. It doesn't matter if you have Optane DC persistent memory or not. You can do those analyses using Vtune to figure out whether Optane DC could help. Once you have Optane DC persistent memory, we have additional features in our tool to help you profile how well you're using it, right? Just because you plug it in doesn't mean your work is done. You know, when you buy a new platform, it doesn't mean all the performance is there right away. There's still things you can do to tune and get better. Before I jump into this section, does anyone have any questions about the previous analyses that I talked about? Okay. So let's talk about what you can do after you have hardware. If you're not familiar with Vtune, there might be a bit of confusion on this slide, and I highly recommend you attend the hands-on session tomorrow to learn more, or check out our demo outside, but I'll boil it down for you. In Vtune, we have the ability to profile all of the memory and all of the caches on a platform. We can tell you exactly how much time you're wasting because you're waiting for data to come back from your L2 cache, or your L3 cache, or your DRAM. Those metrics have been available in Vtune for a very long time. Those are these bound metrics here. How often are you bound by the L3? How often are you bound by the DRAM? Well, now, with this new technology, we've added a metric for persistent memory bound. This number here is telling you exactly what percentage of the time is wasted waiting for data to come back from persistent memory, or L3, or something like that, right? So if you're a performance engineer, or if you're responsible for performance of any workload, identifying the bottleneck is very important. And this tool can help you do it, regardless of whether you have persistent memory. But if you do have persistent memory, we have metrics here to help you profile how well you're using it. Just like DRAM, persistent memory on a multi-socket system can be local or remote. It can be plugged into the socket that your thread is currently running on, or it can be plugged into the socket that your thread is not running on. And if you have to get data off of the persistent memory or the DRAM from another socket, that's a very expensive operation. And we can profile that as well. So this remote persistent memory metric here, which thankfully is 0% for my application, is how often I'm getting data from the other socket's persistent memory. If you've ever heard of NUMA performance issues, remote cache accesses, remote DRAM accesses, QPI or UPI bandwidth communication between the sockets, those could all be related to NUMA issues, and persistent memory can have the same performance issues as well. We can collect information about the bandwidth of persistent memory. Many people in this room have probably seen memory bandwidth charts. How much memory bandwidth are my workloads consuming? Is that the bottleneck? Do I need a higher SKU to alleviate the memory bandwidth issue, etc.? Persistent memory is similar. There's a limited amount of bandwidth available, and understanding how you're using it is very important. Vtune has the ability to profile persistent memory bandwidth as well. You can see an overtime graph of how much memory bandwidth is being consumed, which package or socket is consuming the memory, and whether it's read or write traffic, right? I mentioned earlier that write traffic is much more expensive. So it's important to understand the breakdown of read versus write traffic in your memory bandwidth. And you don't only get this high-level view of memory bandwidth. You actually get the per object breakdown from the application of which objects are reading and writing from persistent memory, right? So if you have a bottleneck in your persistent memory, you can figure out which objects are doing those reads and writes, and which developer wrote those lines of code that are doing those reads and writes, and go, tell them, hey, you've got bad performance in your code. Go fix this, right? You need to figure out how to use memory more efficiently. You can also zoom in on any interesting area in the timeline, and it will update the grid with the corresponding information. So if you see a dip like this, or you see a spike, and you want to know what was happening during that moment, you can filter the data on that little sliver, and right here it will show you the exact functions that were executing during that time. What caused the performance to spike? What caused the performance to dip? And then find out who's responsible for that. Here's some additional charts and some additional data you can collect with Platform Profiler. If you have applications running in memory mode, you can see DRAM traffic. You can see persistent memory traffic as well, and it's broken down by channel. So the way that you populate the DIMM slots on your platform affect the performance. If you don't have every channel populated, you may be missing out on some bandwidth that's available. So understanding whether the traffic is coming through every channel on the platform or only some small set of channels is very important for performance. We also have the ability to collect the amount of traffic that goes to persistent memory versus all memory, which means DRAM and persistent memory. You want to be using the DRAM more than you're using the persistent memory. This persistent memory is not a faster memory. It is a bigger memory, right? So you still want to be using the DRAM as much as you can, and then the persistent memory is there so that you don't have to use disks, because disks are obviously much slower. This is one slide on Persistence Inspector. If anyone's using PMDK or doing persistent memory programming, check out this tool to make sure that you're doing it correctly. If you're missing the flushes of your data, you can have correctness issues. Your code could not be persistent. If you're doing flushing too often, you could have performance issues. There's no need to be doing that. Use a tool to make sure that your programs are efficient and correct. Finally, I'll wrap up with a couple of quick case studies to show you the value of these tools. This was a case study that was done at SAS, where we had an application that was running on a DRAM memory-only system, and what we were able to do is evaluate how much memory the workload actually needed for its hot working set, and then decrease the amount of DRAM on the platform, add some Optane DC persistent memory, and create a workload that is that the performance is very similar to the DRAM only performance, but the platform is much less expensive. So the total cost of ownership of someone that has this platform running this workload goes way down. If you can use some Optane DC persistent memory instead of DRAM and get similar performance, that can be a big boost to the total cost of ownership on a platform. And the last workload I'll talk about is a big data workload. Some of you may have heard of a Graphx. It's a Spark workload. And what we were doing here was evaluating Graphx on a DRAM-only system. And we were seeing memory consumption going up to 100%. This workload was using all of the memory on the system, and once we started putting bigger data sets into the workload, it was crashing. It couldn't handle graphs of a certain size, and we wanted to know what was going on. We evaluated the workload and found that after a certain amount of time, we saw a huge number of page faults, right? And these page faults are very expensive. It means data is being paged out to disk, and that's a very expensive operation for performance. We could see as the page faults started occurring on the timeline, disk accesses spiked as well. And this is not a storage workload. Everything is supposed to be done in memory. But as you put larger and larger data sets into it, the only choice it has is to put things out on disk. So that's what's happening. We started swapping out to disk, getting page faults, and observing disk activity in a workload that's not designed for storage. We could also see that when the disk activity spiked, the CPU utilization dropped. CPU utilization is very important because 100% CPU utilization means the platform is running at peak performance. If your CPU utilization never drops, then there's no performance tuning that can make it go higher, right? You can't bump your CPU utilization up to 110%, it's already at 100. But when you see CPU utilization drop like this, it means something's going on that's causing the workload to stall. And we're also seeing DRAM throughput drop as well as the paging starts occurring. So we were able to identify that this was a memory capacity issue. The application is using all of the available memory and it's showing high disk and paging activity. It's not bound by memory bandwidth or CPU utilization. So this is an indicator that the application is bound by the capacity of the memory. We added Intel Optane DC persistent memory to this platform in memory mode, and the Graphx workloads were able to scale to much, much larger input sets. So now the same platform can handle much larger data sets without needing to use an additional platform or add more DRAM memory, which is very expensive. And with all of these performance optimizations, it's not just a raw performance calculation. It's a TCO, or total cost of ownership calculation, right? So yes, you could just put the most expensive, best DRAM on every platform, but that's a very expensive platform. Understanding your workloads and understanding whether Optane DC may be comparable performance-wise, but much less expensive, is very valuable when it comes to getting performance and when it comes to total cost of ownership. So just to wrap up, this new technology is exciting, right? It's very new, and not everyone has access to it, but there are things you can do today to figure out whether it could be useful for you. And we have tools and workflows designed to help you do that. Once you have this new technology, our tools also have metrics to help you analyze the performance and figure out whether you're using it efficiently. These tools are all free. You can download them today and check them out. And with that, I'll wrap up, and if anyone has any questions, please let me know.